Great.
No need to restart, but.
Okay. So, also welcome to all the listeners of the recording. So, yeah, so like the second part then will be or the third part will be the traveling wave photometric amplifiers as an application for superconducting things, again, in the coupling of light and matter, so light-matter interactions. So let me first of all start with the motivation and why we're interested in these quantum cascade lasers and what applications we envision there. So, as I guess most of you might be familiar with, there is the terahertz gap. So that's kind of a region of the electromagnetic spectrum that's basically inaccessible by electronics as well as optics. So there's no good coherent source in the terahertz regime. And there's one technology that can actually provide for sources in that spectral region, and this is the quantum cascade laser. So why do electronics not provide any viable sources here? Because like how you generate coherent radiation with electronics is typically transistors, so you're switching. And there is like one instance where you switch so fast that electrons won't make it to the channel transistor. So you won't be able to generate like good coherent radiation with high enough power in the terahertz regime using electronics. And for optics, it's mostly lasers. So you depend on some kind of band gap, and these band gaps are usually material dependent. And it's very hard to find materials with a low enough band gap to irradiate, like also in this terahertz region. However, in quantum cascade lasers, we have like the freedom to engineer the band gap ourselves. So another line of material band gap, we're using a semiconductor-based material system, which we layer, so we could put quantum heater structure with it, and thereby engineer the band gap to our needs. And with that, we can also kind of radiate in the terahertz spectral region. And also kind of here in the mid-infrared region. This is especially interesting in several applications. So there's spectroscopy applications, but one particularly interesting application in the near future could be also communications, because communications, we usually don't use free space optical communications because we have losses, like a lot of losses in the optical regime for lasers, so for typical optical frequencies. So there's no kind of space communication, no satellite communication with lasers because they're clouds, so you don't get the signal. However, the atmosphere has two transparency windows, one at 4 micron and one at 10 micron, that is actually accessible by quantum cascade. So that could be kind of a potential application. And it's also like not as, so the attenuation is pretty low due to aerosol concentration, so it's significantly lower. This can be a potential avenue for the application of quantum cascade lasers. So how does such a quantum cascade laser look like as a device? So it is a semiconductor device, typically grown as a substrate. You have some cladding layers typically, some metal down here. And the actual magic happens in this small active region, which is a sandwich structure of different materials. So it's like angstrom, 10 angstrom thick layers of different semiconductor materials, thereby engineering a potential well and associated energy states. So it's a unipolar quantum well heterostructure laser. And these quantized energy levels in this kind of, here with the Z direction, this is kind of the energy in the Z direction. These individual energy levels serve as the lasing states, lasing transitions for our laser operation. So we use this device and we want to model. Now you need to ask yourself, this is like, if you bias, as soon as you start biasing this device, so you tilt kind of this potential structure, as soon as you do that, you introduce a non-equilibrium kind of state into the system. And what you're usually being interested in is how the electrons distribute according to the energy levels, so these quantized energy levels, and what additional velocities do they have in the in-plane kind of direction. So you're interested in how does my laser behave by the electron by electron. And there are kind of, different ways of achieving that. You can simply do rate equations. So a rate equation would be, well, I calculate out my energy level, so I solve Schrödinger's equation, see what eigenenergies do I have in the system, and then I put an electron somewhere and say, well, okay, in the stationary state, the rate shouldn't change, set the rate to 0, and see, like by for each like energy transition, I can get a rate, I can get different effects in, and balance these rates out to get my final state population. There's not really a lot more mechanics involved here. This is kind of the simplest approach. It gets more involved. So the most involved thing you can do is non-equilibrium series functions. So we have one of the world's experts here, actually, non-equilibrium series functions. So I'm probably not really qualified to tell you more about that. What we're actually doing is something in between at the moment. So we're kind of leaning towards non-equilibrium series function because this is kind of the gold standard simulations. But what we are doing is something in between. We do a case-based resolve, so in-plane energy resolved kind of scattering-based description of the system by a Monte Carlo method. So we use different effects, so that we include different effects into our consideration, calculate the rates of these individual effects by Fermi-Stokes rule, and then take a bunch of electrons and let them propagate through the structure to get like the non-equilibrium distribution. So, and of course, this has a tendency like rate equations are efficient. NEGF is numerically kind of an extremely demanding thing. We're kind of in the middle here, still also way more demanding than the rate equations because we need to follow the trajectories of kind of the individual electrons in there. You do a lot of electrons to get good statistics, so still this is a demanding procedure. And it's not as well parallelizable as the quantum transport itself, because you really need to follow the electron. So it's like you can't really parallelize the path of an individual electron because each state you change kind of, so it's a bit tough. So what we want to solve with that is in the end the Boltzmann transport equation. So we want to get this distribution function, which electrons or how many electrons are distributed among which states. And we do that by seeing how these states change. So these change, the states change by scattering events. So this here is the individual scattering events, scattering an electron from the mth to the nth energy state at a k vector, k prime to k. And we include effects such as optical phonons, acoustic phonons, interface roughness, alloy disorder, impurity scattering, and the numerically most demanding parts like electron-quarter scattering, particle interactions. So we try to include all of this into our Monte Carlo framework and solve this equation by Monte Carlo integration. What can we get from it? So from this carrier distribution, this is basically all we need to judge on the quality of the kind of properties of our semiconductor laser. So what we do is we start off with, so all you need to kind of give me is, if you say, yeah, Michael, please simulate a laser. So all I need from you is basically your material system. So this is like an indium aluminum gallium arsenide, indium aluminum arsenide, indium gallium arsenide laser. So this is the material system. There's some doping involved, and I need the layer sequence. So I have 31 angstrom of like a barrier layer, 30 angstrom of a well layer, 19 angstrom again, barrier, and so on and so forth. So you give me the structure, and what we're doing is we're feeding it to our Schrödinger-Poisson solver, which then yields the energy eigenstates. So this gives us a numerical solver that gives us the energy eigenstates. And then we feed these energy eigenstates to our Monte Carlo solver to solve for the Boltzmann transport equation. And from there, we can get quantities like the inversions. What's the upper laser level population, the lower laser level population? And from there, by some approximations, we can also get the gain of the laser. So you see, for example, this laser is a laser from literature. This laser has a lasing gain, which is kind of nice. It's an unsaturated gain, way above threshold. So you can use this laser to laser at the roughly around 40 terahertz. This is what we get out of our simulation structure. But we get more than that. Because we track all the individual electrons in there, we get like how many electrons travel from one period to the next period. And by that, we can track the current. And we know the voltage that we apply. So we can also get IV current. So we get how the laser behaves electrically out of the system. And of course, we need to validate our system. So this is kind of not like just we do simulations and not wanting to be predictive. We actually want to, we're collaborating a lot with experimental groups. We want to be predictive and say, well, this laser is good, this laser is bad. or they measure something. Can you explain that in this kind of sense? So we want to validate our system. So here you see the IV curve of the laser that's actually given like in the literature here. You see what comes out if we do a simulation without lasing. So here it's kind of losing threshold. From here on, we see that basically from 0.5, like a little bit below 0.5 amperes of current, the laser starts lasing. We get some light out of it. We get some optical power out of it. If we don't include this lasing transition, we get the green curve. If we include it, we are at the orange curve, and this actually pretty nicely lines up with experiment. So we can actually validate our kind of simulations with experiment and can actually say, yeah, well, yes, we are predictive. We can actually, like really from physical structures, simulate a laser, and this laser will behave, if you manufacture it, will behave simulation-like. Also, if we compare the optical power that comes out of the laser, also still just in this kind of picture of Monte Carlo simulations, we're also quite close to experiment. So this all lines up nicely. Now, what we're doing is we want to couple this static framework. So like we also we're not only interested in how the laser behaves as static pulse, we're now also interested in how the optical field behaves that comes out of the laser. So like the electromagnetics. So how do we do that? We now use this static framework, like the framework with our Monte Carlo simulations, the energy levels, and some additional waveguide models. So we also need to have geometry in. We want to couple that to a dynamic simulation framework, where we now actually solve for the optical field that pops out of that laser. So, and this we're doing by a so-called Maxwell density matrix system, or Maxwell block type of equation system, where we have the optical field described by Maxwell's equations and the electron dynamics described by a Lindblom type equation. And to feed this kind of system, we use all the information we have from our static Monte Carlo simulations. So we feed in the energy levels, thereby constructing Hamiltonian for our electronic system, the dipole moment operator, and we get like the dissipative parts of the Hamiltonian by the individual scattering rates that are calculated in our Monte Carlo framework. So all these parts that we kind of extract from the charge carrier transport simulations are now basically used as input parameters for our dynamical simulations. And with these dynamical simulations, we then try to actually see what optical field does. And yeah, we can do this in different kind of approximations. One usual approximation that's used at this point is the rotating wave approximation. So we are only used in field like envelopes. And also about kind of the fast dynamics in the electronic system. So we trace away these fast dynamics in the system. We try to only look at field envelopes here. But this is only good if like the lasing systems are narrow. We have basically implemented both approaches. We have a full wave solver and a rotating wave approximation solver for this Maxwell density matrix approach here, with including arbitrary many levels that will come out from our static framework. And doing so, like we want to now kind of examine these corner case scenarios. So where is the rotating wave approximation not applicable? This happens, for example, if you have a case of difference frequency generation. So difference frequency generation is a way of also generating terahertz radiation at room temperature. Because the problem is, although I said that, well, our quantum cascade lasers can make the terahertz portion of the spectrum available, the issue still is that, yeah, these standard terahertz lasers that directly emit the terahertz, they still need to be cryogenically cooled. There have been recent publications, like in the recent 2-3 years, there have been publications out actually making this accessible by thermoelectric cooling, so you don't need cryogenics anymore. You can use Peltier coolers to actually run these lasers nowadays. But still, it's difficult. To do that at room temperature, one idea was to use the intrinsic nonlinearity of such a lasing active region to do wave mixing, to basically mix down the optical frequency, the optical spectrum that comes out from the mid-IR to the terahertz, because mid-IR quantum cascade lasers do not operate at room temperature. So, but there we have a problem. If we are using our rather efficient rotating wave approximation solver that requires our spectrum in a narrow band, we can't really resolve that. Because now we have frequency contributions in the mid-IR, so like 40, 50 terahertz, and some contributions at like 1 terahertz, or 3 terahertz, or something like that. This broad like spectrum region, this requires a real full wave treatment, and we really need to sample our field like very small kind of steps to resolve that properly. This example is, for example, creating frequency calm in the terahertz region by nonlinear wave mixing. So we basically produce a laser that lasers as a frequency calm, so with locked calm states. And in addition, produces active regions such that it has a second transition lasing at a single frequency. And now we want to generate the difference frequency of the single transition with this calm modes to outcouple them in the terahertz regime. So the difference frequency of the frequency difference of omega 1 and omega 2 will be in the terahertz regime. And this is what we are finally interested in. And so here we really require a full wave treatment. And these are some results shown for exactly this scenario. So here you see our normalized gain of the system. So we normalized it to the losses basically here. And we can see, well, we have experimental data, we have our tight binding simulations, and we see, well, yeah, we get here this window where our comb operates, and here we have the actual single frequency that operates in single mode lasing region. If you evaluate our dynamical framework, so whatever comes out of this Maxwell density matrix simulations, you see, well, yes, we actually have that in our spectrum captured. We have here our strong omega 1 single tone, and here we have our frequency, right? And then all these individual modes, they basically mix, there's some intermodulation going on, and they down mix to the terahertz. So what you have is a locked state terahertz column in like 3 terahertz kind of spectral region. And this is all one-shot simulation. So this is we capture the full temporal dynamics in the full wave simulation and just like displace different portions of the spectrum to capture this dynamic. Another thing we recently did was an actually quite accidental discovery, which led to physical review ladders publication recently, which was super interesting. Because we tried to model, this is now with our rotating wave approximation code, we try to model quantum cascade lasers that are not like Farabi prototype cavities, but ring cavities. And what is usually done to reduce the numerical load is one neglects, so one only considers one propagation direction of the optical field. And then it was reported in this Nature Communications paper that they observed dissipative Kerr solitons, like stable waveforms propagating in this ring. So there was like basically a pulse, a stable pulse that propagated in this ring, which is totally kind of, it's an eigenstate of this nonlinear system, so it's totally unperturbed by the nonlinearities. It's like a stable waveform. This has great applications in sensing because you get an ultra stable combo. So you can really do very good spectroscopy with these type of states. So that was interesting. And we tried, well, can we reproduce this in modeling? Can we reproduce that in our model? So we were running our simulations and our solitons were dying out. So they were not stable. We ran them, they were popping up. We've seen these pulses, they propagated for several round trips, even for hundreds of round trips, but eventually they died out. And this is not what was observed from the experiment. The experiment, they let this kind of experiment run for days and saw it was still stable and propagating. So we couldn't do that. Then what we did is, well, just by accident, our PhD student like Lucas, he activated kind of the full code, which also takes into account like both propagation directions. And in order to do that, the code typically has like several regions that we define. He included several regions with somewhere like that. So as the lasing mode propagates, and what will happen in the laser, basically the laser, if you bias it, then the optical field will build up. And then kind of the different propagation directions, they compete for the available gain inside this active region. So one propagation direction eventually is a little bit stronger than the other just by accident. And this will kind of saturate the gain more. So the counter propagating direction won't have enough gain and will eventually die. However, if you have defects in your cavity, you will of course always get some finite backscatter. So some parts of the light will also kind of propagate in the counter rotating direction. And we have included that, this kind of backscattering. And this solved our problem. So our soliton was stable. So then we asked our experimentalists, so hey, like the authors of that paper, it's the group from the ETH Zurich in Switzerland. So hey, what about your cavity? So how does your cavity look? Because we can only kind of reproduce your measured results if we defect. And they're like, oh, that's an interesting observation because we now remanufactured everything, doing a very clean cavity, and nothing works. Then we looked at our initial device, and yes, it indeed had like a lot of defects. So the backscattering turned out to be actually the stabilizing mechanism, providing a phase reference to the soliton, such that the soliton kind of locks to this back propagating mode, and this stabilizes the solution. So only by including a defective cavity, so like a cavity that is not really perfect, we can have this soliton-like operation. And we compared like our simulations with their measurements, and they're lining up. It's almost perfect. It's one-on-one kind of match. So just the pulse series is like a little bit different, but these filtered pulses that come out, so this is like this dark soliton pulse, so the pulse is going to turn negative, they're stable and they're proper. Also the spectrum, like the gray background here is kind of the experiment, so it really lines up. So we could show that actually a finite amount of backscattering facilitates the interaction between kind of counter-propagating or clockwise and counterclockwise propagating modes. And this self-phase referencing in there, this is a necessary ingredient to have for stable, durable soliton propagation in numerical methods. And basically also in reality. So we kind of confirmed it that, well, a clean cavity is not always what you want. Although the experimentalists aimed for it, but they showed, well, if we have it, if the cavity is clean, there's no later. There's no kind of solid propagation. So with that, this was actually a huge success story. And yeah, we were able to publish it in PRL last year, basically. Another thing we observe is techniques for passive mode locking quantum cascade lasers. So typically to achieve short pulses in lasers, there is the famous House relations. So a short pulse typically is considered being impossible in a medium or fast gain recovery times. That's kind of typically what's happening. So what we've done is we wanted to try to show if passive mode locking, so generation of very short pulses, is possible with terahertz quantum cascade lasers, which are devices with a fast gain. And what's usually done to achieve this passive mode locking is including a saturable absorber in there, where the group from Miriam Vitiello in CNR in Italy uses graphene as a saturable absorber, basically graphene put on top of the laser to absorb the light and thereby form kind of gain loss windows, form short pulses. We implemented kind of a loss model then for graphene into our code. And we've seen, yes, indeed, short pulse generation should be possible. And what plays an important role here is kind of the enhancement effects at the reflecting boundaries. So you have reflecting boundaries. This is again like rotating wave approximation code, which just have envelopes propagating here. If a pulse comes like from the left to the right, you see, well, we have plotted here gain and losses spatially resolved. You see that the gain for the right propagating mode is like a little bit above the losses. So you get a net gain window for your system. And the counter propagating mode basically just experiences losses. It's always kind of below our loss threshold. The loss also is spatially dependent because you have a saturable absorber and the intensity of the field will saturate the absorber. Therefore, the loss is spatially dependent. Then the pulse propagates, hits the boundary, and at the boundary, the E field gets reflected. So you have field enhancement boundary, and the pulse flips over. And what happens, and this is like the interesting part that makes these short pulses possible, is that the gain windows now here overlap due to this like field enhancement. Thereby, you saturate the gain more at the boundary. And this then accounts for, again, a gain window now for the reflected field. But the right traveling field gets basically kind of losses here. And also the tail here of this pulse of your spatially resolved, of your propagating pulse will experience losses. That means due to the saturable absorber, pulse hits, gets like reflected at the boundary, have a field enhancement, you saturate your absorber more. This will lead to a net loss window here for your reflected pulse, effectively dampening all components that will broaden up your pulse. So you keep a very kind of narrow pulse shape, and thereby having a passive low blocking, having basically short pulses in the terahertz. That's kind of, we could with these kind of simulations confirm that like short pulse duration is possible, and this graphene saturable absorber should be a viable way to achieve that. And end of 2024, an experimental paper was also coming out from that Italian group demonstrating. So what is kind of the future directions? I mentioned as applications, communications. And for communications, we want to have a quantum cascade laser source that needs to be modulated some information carrying signal. Because we're not only interested in lasing, we also want to modulate data on top of that and get like simulation strategies and how we can do that. And in order to do that, we need to bring this information carrying signal, which is typically in the microwave regime, on top of the laser. How is this being done? Well, we need to bias our laser. So we usually have a bias T. We bias our laser, and then we modulate this laser bias by our information carrying signal. And if you look how this laser ridge here basically is kind of manufactured or done, this is kind of similar to a microstrip waveguide for microwave kind of applications. So what we need to do is we need to model this laser here as, first of all, as a laser, of course. And a second part of it will be modeling it as a microwave transmission line by doing some additional transmission line equations that we couple back into Maxwell-Bloch equations, Maxwell-Bloch system that describes the kind of lasing interaction. So what happens basically is that the microwave signal will propagate on this transmission line here. It's open at one end, so we'll get reflection here. So we'll get some standing wave behavior on top of the laser. So we get some microwave optical co-propagation. So we will modulate, depending on space, we will modulate our kind of laser differently. And we want to include this in models such that we can do proper modulation with our laser and see how this kind of works out in the future. This can then, for example, be used for secure communications. This is kind of a scenario that was also recently presented in the literature where you have two QCLs. You couple those two QCLs. This can be like a very long separation distance. You couple those two long cascade lasers together and do some sense of private communication because you modulate one of the lasers, shine one of the lasers into the other, and you're only being able to retrieve the information carrying signal, like this bit stream, this modulation data, if you know both kind of data streams here at the detector, emitter coupling Telluride detector 1 and 2. So if you only know one, you basically hide your information in chaos. So it's a chaos kind of hidden private communication scenario where these modulated quantum cascade lasers can potentially be used. Okay. Enough quantum cascade lasers for now. Let's kind of talk about the general modeling approaches we're trying to employ here. And this is now an approach which is kind of contrary to what I presented in the quantum cascade laser. So in the quantum cascade laser, what we did was this Maxwell-Bloch, Maxwell density matrix kind of simulations. What happens there? There we have a quantum model for the device. So we model this like this electronic system as a multi-level quantum system by the Lindblom equation and couple this quantum device to classical Maxwell equations for the field propagation. Now we're basically interested in quantum features in the light itself. So what we're doing is just the opposite. So we're now modeling the quantum system as a perturbation, like as a bath basically to our kind of system to get some coherent gain into our system and model and model the optical field that's propagating in our system quantum mechanical. And we're getting like also from our gain material, we're getting several kind of nonlinear effects, which is like third order Kerr-like nonlinearity in our system, which will give us additional kind of field features, which is degenerate forward mixing, non-degenerate forward mixing, and some means of self-modulation. So we're now looking at how the individual modes, the individual lasing modes in our laser interact with each other from a quantum perspective. Because then we are ultimately interested in, okay, can we from here devise some kind of measures on how much, for example, a photon in this mode is entangled with a photon in another mode? So can we devise some second quantization kind of measures? So we are having this huge Hamiltonian to do that, and we can phenomenologically include gain and loss as baths in that system. We'll get some damping and we'll get some gain. The question is how we run these kind of simulations and what do we want to get out of it? So we usually want to get like the evolution equations for each of the modes. This can be usually derived by the Heisenberg equation of motion of the system. And then we want to get, for example, second order correlation functions. To see whether we get like photon behavior, entanglement, like if this is smaller than 1, it's usually regarded as like it indicates squeezing or photon anti-bunching in the ith mode. So what we need here is a fourth order moment, or fourth order statistical moment of these quantum creation and annihilation operators divided by second order moments. Okay, so we can get these equations of motion for these moments by plugging them back into our Heisenberg equation of motion and evaluate the Heisenberg equation of motion. However, that's a tedious task. That's a really tedious task. So evaluating these equations, I know we have done that already. It's a pain. So we can do this in a kind of structured manner. We can say, well, let's derive all the equations that could possibly appear and summarize the operators that would appear in different orders. So we have first order operators, which is basically the expectation value of the creation and annihilation operator. Your second order operators, which is the number operators, and second order correlation functions. And the third order operators, and so on and so forth. And then can kind of come up with an equation how the time evolution of a certain class of operators, so like operators of first order, second order, third order, depend on all the other orders. And that's basically a system of equations that we can't really solve because it's like infinitely many orders. So it's an infinite hierarchy problem. It's an infinite hierarchy of moment operators that are coupled to each other. And in order to solve that on a computer, we need to come up with a certain truncations. So we need to find a way how to represent moments of kth order by just moments of k minus 1. Not any higher orders, such that we truncate of kth order in statistics. Right? So this is what we need, and then we can solve it. And we can kind of write the computer code and do it. That's what we thought. It turns out it's not. Because this has some quite weird scaling behavior. So if I'm just interested, for example, let's look at this column here. If I'm interested in just 10 modes, right? 10 of these modes, I want to see all these interactions. And I am interested in moments up to fourth order to being predictive of G2 functions, right? If I do that, I would already require like 50 gigabytes of memory, roughly, just to store these matrices, these coefficients. So the memory behavior scales terribly. So reality, like in real comps, you're interested in hundreds of modes. So this scales into the exabytes of memory. So this is not really easy. So we need to come up with a strategy that helps us in describing and still solving this equation. And what we can use is the fact that these tensors that couple all these individual modes here together, they're usually sparse. So only a small amount of entries will differ from 0. However, it depends on the nonlinearity in the system and on the order you want to do, which ones are 0. So we need to just identify those equations that are needed. And the idea was now, okay, let's make use of real symbolic calculations to do that and systematically identify only those equations that are actually needed to be solved. And for that, we were looking for a numerical tool, or for a computer tool to do that for us, because as I said, it's tedious to derive all these equations of motion. So we browsed through all available different kinds of tools. There was like quantum tools like Q-tip, KISS-tip, but none could handle that. We browsed symbolic math libraries, we browsed Mathematica, which didn't really handle like commutating stuff really well. And there was SymPy, which is a Python library that is kind of exactly there for second quantization operations. And Python even like has this second quant kind of library, this module, that can do that. However, it only at the moment, it only supports fermionic operators. So our idea now was, well, use the second quant library and extend it to also support bosonic operators for our purposes. So at the moment, if you just do this simple like 5-line code, you import the symbols basically, and you import the second quantization library, and you just want to normally order your operators as we have them here. So we try to get normally ordered operators, daggers to the left here. So you just want to perform this simple operation to build your hierarchy base, right? So you want to put daggers to the left and evaluate the commutation relations accordingly, basically. This will be this code here. But if you do that, if you apply this Wix to AI a dagger I, what you want is a dagger j AI plus a 1 if I equals to j, for example. If you run that, you'll get a not implemented error because this module doesn't support bosonic operators, only fermionics with anti-commutating operations. So what we did is we now implemented that. So we have implemented this extension into SymPy's second quant module such that you can run that. So you can do it, you can run Wix, and you will get the correct ordering plus the chronic adapting, such that this actually works. So now we can use that to then systematically identify, well, okay, I derive an equation of motion, put all the daggers to the left, make my ordering right, then see, okay, I have an equation of fifth order with a dagger, a, for example, and see on what other variables this depends. Calculate new equations of motion for these other variables and truncate at some point. So we can find a closed system of equations that we can then numerically solve. And this is way more efficient or reduced than solving like the full kind of tensor system. However, these smaller computations still take a while. They're not really efficient. There is something rather brand new. I think the publication date is actually in August. If you look at this package here. It's in computer physics communication. There is like a new package, Pibolano. This is kind of a package that implements kind of the same feature, but in a more efficient way. So this is kind of something I want to try out next week to also use this package to be quicker with us. Another approach we're looking into is, well, as I said, we use this Maxwell-Bloch metal density matrix kind of system to describe a quantum system that couples to the electromagnetic field. However, there, one has to use the electromagnetic field stream classic. What we look into is we want to combine these semi-classical simulations, which are rather efficient. You can run them still probably still cluster, but you can run them on not so expensive machines. So you don't need huge clusters. Single nodes, 2-3 nodes is just enough for them. So, but however, what we want is we want still field quantization in facts being measurable or being detectable using these semi-classical methods. So the idea is to extend the framework of our Maxwell-Bloch equations by some quantum corrections. So the quantum corrections or the quantum mechanics will do some statistical kind of modifications to the results of our electric field that we get out of classical propagation. And we want to bring these back in to the Maxwell-Bloch equations by some kind of stochastic corrections. We call them the stochastic Maxwell-Bloch equations. And the route we went there is to do like a full quantum mechanical kind of description, put some dissipation in, and derive some Fokker-Planck equation, and from there some stochastic diffraction equation to get the proper quantum statistics out of the system. And then did a kind of a transformation of this Fokker-Planck equation system, such that it has the same form as the Maxwell-Bloch equation system, just with some additional terms that drop out of the quantum, the kind of the correct quantum statistics. And so we kind of implemented stochastic equations where we can do multiple classical runs, like runs of classical equations, with added noise terms. Then you can average and get kind of the quantum behavior out. And this is like still quite early stage research, I would say. We published a paper last year on that. And here we basically just looked at the simplest possible system. We looked at the full wave James-Cummings model, where we couple an atom, like a two-level atom, just to a single mode of lasing operation. However, in a full wave treatment inside the cavity. And look at basically some Rabi oscillations. This is kind of what's coming out of full wave treatment. And this kind of method is simple enough such that we can do like a full Hilbert space expansion with enough states such that we can get a reference solution. So what we did is like looking at the populations and the coherences in our density operator. We can also do the same thing in the field. And we can look at, for example, what Maxwell-Bloch will give us. And Maxwell-Bloch, like the kind of semi-classical approach, will give us the dashed dotted line here. And the actual, the actual Hilbert space expansion solution gives us the dashed line over here. So this dashed line is the actual quantum solution. The dashed dotted line is what the semi-classical approach will deliver. And the question was now, okay, do our corrections, our statistical corrections to the Maxwell-Bloch equations drive the system in the correct kind of way, such that we drive it to a more quantum state? And the answer is yes, indeed, it does. So this is kind of the solid line you see here is now the full quantum mechanical, or the full quantum mechanical. The dashed line is the Hilbert space expansion solution, and the solid line is this stochastic extended kind of Maxwell-Bloch type simulation. So we are more in the kind of regime where we say, yeah, this is kind of closer to the quantum solution than it's the classical. It's not a one-on-one match because you would probably, for a one-on-one match, you would need to run more simulations to get better average. So that's basically what we've done. So we could kind of trade, in a sense, memory with computation time. So we can like run a lot of semi-classical simulations, which are not so expensive, but they don't require as much memory, like it's like one full Hilbert space expansion solution will do. And by averaging those solutions, we can get the full quantum mechanical state. That's kind of our proposed method. It, however, suffers from still a lot of kind of problems because if I would extend the simulation time here, eventually I'm going to break down because these statistical methods become sometimes unsafe. So it's not good yet. So we still need to invest quite some work to get this running. But my student Johannes is doing a really good job in getting this up. Well, and this then finally brings me over to the third part of the presentation, last part, which is now superconducting kind of systems, which are, however, kind of described with similar tools. So we can reuse a lot of what we've learned like before in this area. Because like the symbolic numeric framework can very well also be used to describe the quantum mechanical behavior of these troubled electromagnetic. So it's all kind of like that. Although the devices are rather different. So kind of to get you all into the application once again is like, what is this traveling wave chromatic amplifier like and where are they used? So who of you is familiar with qubit readout? One? I know, yes. So most of you, I guess, are. So I'll go quickly over that. So how do we read out quantum information of superconducting qubits? You have a dilution refrigerator where I have this cartoon here on the right. And in the actual quantum processor where all the magic happens is down here at the lowest temperature stages, 10 to 20 millikelvin, right? So we have this quantum processing unit here. You have your qubit, which is like in most kind of current topologies, it's a transmit qubit that's coupled to a readout resonator, like the one there before, like resonator, off resonator, and you load it with this qubit. So what happens is, depending on the state of your qubit, the inductance of this Josephson junction, which shorts these two capacitive islands, will change, and thereby loading your resonator differently. So your resonator will have a different resonance frequency depending on the state of the qubit. And now you want to probe that by sending down a probe pulse, which is very, very weak. So it's attenuate down here, where it is just like some tens of microwave photons, coupled to your resonator to populate your resonator and get some dispersive shift here in this transmission line. So you change your pulse slightly depending on whether the qubit is in the 0 state or the 1 state, and you want to detect kind of change the pulse, whether the phase shift or amplitude shift. You can decide in different ELAP scenarios. However, you want to detect it using classical equipment. So you want to do that at room temperature with a electromagnetic lens. The issue now is, we have here 10-ish microwave photons. So we need to amplify. And we can't just bring like a normal transistor-based amplifier down here because we don't have enough cooling power budget. They don't kind of operate well. They add too much noise. So we need to have like an amplifier system that will be one limited in terms of noise, so we don't add too much noise to our system. And in addition, being like not really dissipative, such that we don't heat up our lowest temperature state of dilution with it. And this is where these traveling wave chromatic amplifiers come into play. So here's some like physical realizations of these devices. And they basically consist out of transmission lines with periodically embedded Josephson type nonlinearities. And you can use them for wave mixing. So you send in a pump tone. Again, we're back at four-wave mixing that we've seen before. The pump interactions, the pump mode interactions, that's something similar. So you send in a pump tone, a strong classical pump tone, and you want to nonlinear, let it nonlinearly interact with our small signal that propagates through here, and then destroying energy out of this pump mode, bringing it back into our signal mode to amplify the signal to have. And then amplify further using plastic technologies, higher up in the readout channel. This can also be used, for example, for the quantum elimination protocol, just another application. So where we use this traveling wave chromatic amplifier, again, as a nonlinear wave mixer, as an entanglement generated, generating an entangled kind of signal hydro photon pair, where you send one to your target, receive it, retain the second one of this entangled pair delay line, and do some correlation detection, which in this quantum elimination protocol, I'm personally not a huge fan of this protocol, will give you a 6 dB advantage in the Chernoff error bound compared to the state rate. And these traveling wave chromatic amplifiers could also potentially be used here as entanglements. So what are we doing now? We are collaborating with experimentalists to propose better designs to make these amplifiers better. So harder, better, faster, stronger, we want more gain, less noise, better amplifier. So the classical kind of things, like what we also see here in these pictures, we use a single Josephson junction and embed it along the line, and use some means to do proper phase matching, such that the velocities of the pump mode and the signal mode are kind of similar, such that we don't run out of the phase matching condition. Because like all phase match, we don't get application. What together with the experimentalists, we came up with a different topology, which is a snail-based traveling wave chromatic amplifier, where you don't use a four-wave mixing nonlinearity, or if you try to use a three-wave mixing nonlinearity, which in theory is more efficient. And in addition, one huge problem in these traveling wave chromatic amplifiers is you typically send in the signal and pump mode at the input port of this amplifier. So they travel through the amplifier, and the strong signal will actually be somewhat close to the critical current of these junctions. So there's a limit of how hard you can pump that, right? Which inherently limits the gain. And it's also hard to separate the frequency contents of your pump mode and your signal mode. Because it propagates along the line, you'll have the gain maximum kind of close to where your pump frequency is. So you can't basically use the portion of the spectrum where your amplifier has the largest gain. So the idea was, we do a so-called flux pumped traveling wave chromatic amplifier, where we have an additional transmission line, like a classical linear transmission line, where let the pump signal propagate through and magnetically couple kind of the signal that propagates in this transmission line into our nonlinear elements, which have kind of a loop-like geometry, thereby catching some of the AC field propagating in this transmission line, and thereby pumping our snail. Kind of basically non-linearly changing the operation point of the snail, and changing this operation point will then lead to a free mixing interaction with the area. So that was the idea. And now let's take a small closer look onto that. So we try to find a model for that, where we have a Hamiltonian that consists of linear propagation right now, this three-wave mixing. We still have residual four-wave mixing, which kind of is the cross-phase modulation part, and we have losses and kind of bath couplers or a heat bath representing the substrate losses down here, and coupling to this loss. Again, we use the same methodology as before. We are interested in mode creation and annihilation operators of the system. So in the Heisenberg picture, we want to investigate what's the amplitudes of a signal propagating through the system, and we derive that by solving Heisenberg's closed motion, and by applying quite some rather standard approximation. So, for example, a strong pump approximation. So assuming that our pump signal is way stronger than our actual signal amplifier, assuming that this is a classical mode, which is just kind of represented as a number, and it will not be depleted. So this kind of violates energy conservation, but it allows us to construct a solution. So we assume a strong classical pump approximation, and we can then kind of derive an approximate system of equations, which we can then solve analytically. This is what kind of Thomas said, we have sophisticated analytical models. And of course, again, we need to measure. So we need to see how this analytical model behaves. And we did that, for example, for a traveling wave chromatic amplifier structure from the literature. And compared, for example, the gain. So the gray kind of background here is the experimentally measured gain, and our dashed line is the gain that we get out of our literature model. But what I'm way more proud of is the blue line here. Just zoom in here, basically, because this is the added noise of the traveling wave. It's quantum limited added noise. So this here basically tells us how much noise photons equivalent to the input of the amplifier does our amplifier add. And this is like, we can get the gain curve by classical considerations. We can't really get that by classical considerations. And again, we use the same reference here because they provide all the parameters we needed for a circuit kind of type of model. And we can see that our predictions for the added noise actually lie perfectly within their measurement. So we are kind of confident that this model is kind of true and can be used for finding now better designs of traveling wave parametric amplifiers. And by that, to find like better designs for the snail-based parametric amplifiers, we can have a look at the overall global design space. So what's the degrees of freedom? So how can we optimize these amplifiers? What can we change in our structure? We can look at that and basically plot the design space. So what is the 2 degrees of freedom we have for one unit cell? We can, for example, change, so keeping now the number of big junctions in the snail fixed. So snail stands for superconducting nonlinear asymmetric inductive element. And it basically consists of a number of large junctions in parallel with a small Joseph. Right? We now assume that we keep the number of junctions fixed. That would be another degree of freedom for our design space. It's like an integer degree of freedom. And what can we change here? We can change the asymmetry ratio. So how asymmetric do we make these 2 junctions? So what's the number of alpha between 0 and 1? Compared, this is kind of the critical current of large junctions compared to big junctions. So we can use that like as a degree of freedom. And another degree of freedom is the operation point. So the external magnetic field bias. So how much flux do we thread through kind of this loop in order to drive this into a certain operation point. So this is the 2 external degrees of freedom. We can, one is kind of device specific, the other one we can still modify, we can apply different magnetic flux. And we can map this out. And then we can calculate the prefactors that are responsible for our 3-wave mixing and our cross-phase modulation. So basically we can calculate this chi here, and in the phase mesh there, phase mismatch there is the cross-phase modulation. So we can calculate out these prefactors. And we calculated out these prefactors, the gain coefficient and the cross-phase modulation coefficient. And our condition now is, well, cross-phase modulation is definite. So we actually want to have 0 cross-phase modulation in our tuple. And then the red line I kind of highlighted here are all the points in this whole design space where cross-phase modulation is exactly equal to 0. Then we basically transferred these number of points to our gain coefficient. And now the task is basically selecting one point on this line where the gain is reasonably large. Again, there should also be additional kind of consideration. So we didn't choose the point up here where it's the largest, the smallest, the absolute largest, just right. So we didn't choose this point here because here we are in a point that is very kind of susceptible to small fluctuations. So we have, if we're in this point and we kind of don't hit the parameters perfectly, we are kind of already in a regime where we don't want it, or we have a lot of processing, right? So we choose a point somewhere here. So it's actually, we chose a point at 0.012, so at 0.12 alpha, which is kind of here, which gives us a very stable regime for the two-point manufacture. Then we kind of extract the parameters out of there and let these parameters run through our analytic model, and we predict a very large gain of roughly 20 dB. So just to remind you, we had 10 dB before. So this is kind of a single junction two-pot. This is not kind of the device we have here. This is just if we had a single junction four-way mixing. That was what was implemented in the experiment. That was what we implemented in our theoretical model. Here we now have these snail-based traveling wave parametric amplifier structure, where we actually now put these kind of superconducting nonlinear aspect conductive elements, and we get a way larger gain and even lower added noise out of our model. Modified our model, got that, and then went to our experimental partners. This is the Walter Meissner Institute, also in Munich. We have funding together, we have a project together in order to build these amplifiers. And then we translated the circuit parameters we got out of our model into an actual physical implementation, into a physical device. And this is one of the prototypes that we have. You see here the pump line, and here is the actual nonlinear transmission line. These kind of gratings that you see here is basically a capacitor. It's needed to achieve a capacitance here, a ground capacitance that's large enough to have this transmission line matched to 50 ohms, because the impedance of this snail, like the inductance of this snail, will be rather large. So in order to have this kind of match to 50 ohm, we need a rather large capacitance. So this is kind of a fishbone type of capacitor at this transmission line. And then we want to run these kind of structures. Fortunately, we don't see an experimental curve on the background here. This device kind of works. It only doesn't produce 20 dB of gain, but rather 4 at some frequencies. And this is due to a lot of issues with these structures. So what we want to do in the future, and also working a lot together with Thomas, we want to get a better understanding of the actual system and how good they kind of perform. Because the manufacturing of these junctions is actually a mess. So they are manufacturing a lift-off process, and no two junctions are ever going to be the same. We always, in our analytical models, we assume perfect matching. Everything is kind of nice and beautiful. It won't happen in reality. So we need to do some careful modeling of process variations. So parameter targeting is an issue. Therefore, our devices at the moment don't work. Can't show you any experimental results. But I can only say we're working on it to get better in modeling and more data from so we're getting weird reflections and all of this stuff out of the system. Good. So in conclusion, what have we shown you? We have revisited models for quantum cascade lasers, general models for kind of quantum light matter interaction, where we introduced new models and with these stochastic corrections for the Maxwell-Bloch equations, and a black box model for trailing wave parametric amplifiers that are kind of 3 different perspectives that all come together in this wave mixing kind of thing. What's the future work? Yeah, well, we want to kind of use these quantum cascade lasers for mid-IR communication. So we want to get actual channel models for these devices. We want to better verify our stochastic differential equation model for semi-classical and full quantum, so semi-classical modeling of full quantum features. And we want to get like our trailing wave parametric amplifier design up and running position. Really works also in experiment. So that's the short-term goals of all this research. And with that, thank you for your attention and for giving me for an hour.
Do we have any questions for Michael? Yeah, Tom.
I have a curious question. I think it was in slide 12 for the QCLs when you had the ring shape thing.
Yeah, this here.
Yeah, 11 day.
Yeah.
So when you simulated or when your student simulated
Lucas,
that, did he use periodic distribution or regular distribution of defect?
Yes, he did actually. But we also, so very good question actually, because this changes something. So the thing is, so he basically simulated the first point he simulated, like the first simulation was done as here. So it was kind of a regular periodic kind of structure. So you have periodic interfaces where you get reflections. But then I said, well, this can be difficult because this can have some resonances, right? So you can have some coherent kind of backscattering. So we then redid these simulations by some Rayleigh kind of backscattering, where we did like random backscattering. The core message is still the same. The soliton gets stable. What is a necessary condition, basically, to have a stable soliton is that you get a coherent phase back radiation. So what needs to happen is, well, the back propagating mode won't see any gain because the gain is eaten up by the, oh shit. The gain is eaten up by the forward propagating. What is a necessary condition is that the reflections they should kind of provide a phase reference. So the reflection will experience loss and it is not allowed to die out completely before kind of the next reflection region is coming. So if we have distributed backscattering, but it's kind of gradient type backscattering, this will work. Yeah. Just the curves look more ugly, they're very noisy. So we have additional nodes in there. This is kind of not what the real thing is, but it's the
So does it mean that the defects would have to be, well, from the perspective of the photons, far enough apart?
Yes.
That you don't have collective modes.
You don't have collective modes standing up. Right. So I think that's still not what happens in the real device. In the real device, it's more of a kind of you get like a different kind of refractive index in here and out there, and this kind of defects, they're more continuous. So you get a kind of a continuous back reflection. Yes.
Well, as long as you have variations locally, they're not
right
creating the collective modes.
Right, exactly. You don't want to have collective modes. This is a systematic problem. And exactly, so we did kind of this first simulations that showed that actually, as you said, were like periodic things, but we redid the simulations. That was actually also required by reviewer from that paper. Because I mean, he's right.
It wasn't me.
That was also required by reviewer for this paper, saying, yeah, well, hey, be careful. We have like periodic kind of modifications. And yeah, he's right. So we redid it, and it also appears as long as so basically the message is as long as the back propagating mode still has some phase reference, kind of isn't dying out completely in between two kind of reflectors, in the soliton stabilizes.
Just to mention it, it's something we see in electronic properties as well. When you have defect states and you distribute them periodically, you get very different results, and it's somehow random when you break the symmetries. Mm-hmm. So happy to see that it's the same.
It's the same. It's exactly the same.
Yeah.
How are these defects with these engineering? I know that in
this is not like they're not engineered, like they're just there by accident. So these defects are there by accident. So we don't engineer them at the moment. There's actually kind of a project going on at the moment on the experimental side, so we're not directly involved in that, of basically recreating this behavior by manufacturing this clean cavity here and using focused ion beams to like engineer defects in there to kind of reconfirm that this is actually the case. So at the moment, what happens is they kind of manufacture now, there's no paper out yet, not that I'm actually, but I know that the Swiss kind of people, the Gerald Weiss group is now doing that. They're having these clean cavities of the same device, and they're then shooting like with a focused ion beam, kind of implanting defects into the structure to revalidate kind of what happened. But yeah, what it will be then in the end is a defects engineered by Photonics.
How are these manufactured? With the manufacturing machine?
The devices here at all, it's a difficult process, actually. It's like molecular beam epitaxy typically. So you have a substrate, then you do MBE growth of the individual layers. It's typically then MOCVD growth of like the cladding layers. Then you kind of do some chemical etching or some physical etching of the laser ridges, then typically transfer them onto the substrates. For the fabric rows, there's typically some cladding, just to kind of cut the interfaces. For the ring types, it's typically some etching processes.
Right, some questions on the kind of Monte Carlo processes
Yeah.
that you're using. So you had different strategies using Monte Carlo, or maybe the stochastic differential equation, was that not truly Monte Carlo?
It was not truly yeah, it is in a sense Monte Carlo.
Right,
So for the Monte Carlo simulations for the QCL, this is a completely different program than like the stochastic MBE. The stochastic MBE is basically, it's an Ito type differential equation you derive from the Fokker-Planck equation of the density matrix, basically. So you derive this Ito stochastic differential equation. And what we came up with, basically what Hannes, PhD student, came up with, because he's a trained mathematician, and that's quite worthwhile in this research here. He came up with a transformation transforming the form of this Fokker-Planck equation into an equation that basically resembles the Maxwell-Bloch equation. So he identified kind of the same terms in the kind of either type SDE for the phase space variables than you would have in the MBE, in the Maxwell-Bloch type equations. So he identified similar terms, and that's like, okay, well, here's the electric field, here's the electric field, here is like the coherences, here's whatever. And there's this additional terms, and these additional terms depend on these Ito like Gaussian random variables, like those Wiener process increments, basically. And these are kind of now these corrections that are added on top of it. And to kind of get the solution out of these Ito type stochastic differential equations, what's usually done is you run them several times and average.
right, and so that's kind of what so with the quantum cascade lasers, it sounded like you were saying that kind of Monte Carlo approach is not very parallelizable.
No.
But then for like these stochastic ones.
This is indeed parallelizable,
Okay.
because like each individual run is independent.
Right, and so
So,
then the question, I guess, was how many samples are you typically needing to take
For this thing here, it's 1,000 cells.
Okay.
1,000, so kind of, it's 1,000 runs.
Sure.
Oh no, this is. I need to reread the paper, because
well,
I think it was 1,000 runs for this, or was it if I tasked Johannes to run 1,000? Yes. I'm not sure.
I mean, any paper that you see doing a Monte Carlo method, it's almost always 1,000.
Yeah,
And then
I think this is 1,000, actually.
I mean, have you guys looked at any like acceleration techniques, like in kind of traditional numerical methods? We think of
This
Monte
is
Carlo
totally-
as being like a
This is
very
only
slow.
This is a super naive MATLAB implementation, and without any kind of acceleration yet. Because the thing we wanted to show is actually, hey, well, we can actually find something that kind of corrects the ME equations.
Mhm.
The thing is, we didn't look at acceleration techniques yet, because that's not like, speed is a huge issue, but it's not the biggest issue. The biggest issue is the moment stability. Because I've shown 3 kind of time units. It's kind of all normalized units at the moment here. I showed 3 time units here for a reason, because if we go further, the simulations will blow up at some point.
So like numerically unstable, like exponential growth, or
Not really
just
exponential growth.
not agreeing with
Because
that?
it agrees up to a certain point, but then these stochastic samplers, I think it's like due to these phase space methods and stuff. Like what you do is you follow basically a trajectory in phase space for these phase space variables kind of system in the Fokker-Planck equation kind of system. And the issue is you have some error accumulation in there. And this basically causes, so you typically have 2 kind of should be complex conjugate quantities. You treat them as independent variables because then you get the positive p representations, you get like actual statistics, otherwise you won't be able to do the statistical sampling, you would get negative probabilities. So with a positive p representation, you get kind of probably like real probabilities, positive probabilities. But the issue is what happens is these kind of independent variables then become further and further apart from being complex conjugated to each other. And so this adds up to being non-physical. So
Are you just using like a Runge-Kutta kind of integrator? For
the solution, like integration solution here is a Runge-Kutta type of feature.
Well, go ahead, I had to read
Yeah.
So then because it's talking about this modeling of quantum devices, right?
Yes.
So from first principle perspective, you feel like when you're trying to measure the match agree with measurements, right? Then all the physics well understood, or you found that there was some new physics that
Really find new kind of physics. So the newest kind of physics we found was like this self-referencing kind of mechanism in the soliton stabilization. But that is kind of, it's inherently there in most devices. People just didn't give a look, or they were not like interested enough to understand it. But it's not like we came up with something totally new and not kind of described anywhere in the literature. We didn't find any new kind of physics yet. So
I see. So then the physics you feel that is theoretically is well understood, but the modeling is difficult.
right.
Uh-huh.
Right. So the modeling is difficult, and I mean, I'm also not a huge fan of. So I think we need to do better in the modeling. I'm also not a huge fan of all this kind of. I'm not a huge fan of mode decompositions. Let's call it that. Let's call it that. So mode decomposition, which are typically employed in all of quantum mechanics, it's for time domain kind of type of simulations. This is, in my opinion, not the way we should go to. We should probably go more to field-based quantization kind of techniques, or like potential-based quantization techniques, to see better kind of numerics. So I'm not a huge fan of what we are actually doing here. So I think we should kind of step one step back and reconsider the choices of our fundamental.
So then you had those data shows excellent, that's very impressive, agreed with metadata. So then those kind of correction term you added, or some like a new some physics term capture certain physics, those analytically derived or the
You mean this kind of thing here?
yeah.
I mean, the interpretation of that is actually super interesting, because it kind of yields you like, or it kind of points you towards a new way of thinking about quantum mechanics, because it's like, okay, I have the semi-classical equations, they evolve in a certain way, so this is kind of the dashed dotted line, and I have the full quantum equation that evolves in a slightly different way, actually. So what's the difference? The difference is, if you transform it into the form of the stochastic Maxwell-Bloch equations, the difference is just these noise terms that are added in each time increment. So you kind of have your Maxwell-Bloch type equations, you have a time increment, and in each time increment you add some fluctuations to the system. These fluctuations will have some mean, they will have some variance, they will have some higher order moments. So whatever statistics that drops out of quantum mechanics. But what kind of this kind of simulations show you is this here is actually the difference it makes. So like semi-classical type of simulations and quantum mechanical type, full quantum type of simulations, they differ by exactly this term. This term, it's a stochastic term, so it's not like really you can say anything analytical about it, like get an intuition about it. But these fluctuations, this is the randomness of the quantum theory. So you can kind of directly have it encoded in this form. That's the beauty of this kind of approach, I would say. So it yields to a different view on it.
Thanks. Related to that, I think it's in slide 20 where you showed the memory.
Yeah.
Is it obvious that the memory blows up that hard? I mean, I'm thinking of a two-particle Green's function. Again, sorry.
Naive approach, yeah.
I think you would have 100 degrees of freedom times 4, so this is a 10,000 by 10,000 matrix. That would be, of course, easy to handle. So where do you get the petabyte higher?
So what we did here is basically just naively investigating this tensor here. With a truncate, okay. I probably didn't tell you about the truncation rule yet, but I mean, okay, the truncation rule is we say, okay, the most naive truncation rule is, well, let's write down fifth order operators by fourth order operators times the first order operator, so some things like that. So you can incorporate this truncation rule, and then basically you just count degrees of freedom. So you count all the I1s, A2s, A3s, A4s. So A4 you have, again, like all the possible increments. And here you see, this is all IJK, IJK, IJK. So this is kind of the 3 mode indices. So if you say we have 10 nodes, for example, you have all IJK possibilities. So it's kind of the, so this can be 1, 1, 1, 1, 2, 1, and so on. So, and you do this for all of it.
For all the combinations.
For all the combinations, for all possible combinations, and you do this for all possible interactions. So, I mean, each evolution equation of each interaction can depend on each other interaction, and that's what. So that's the scaling behavior. So that's how we. This is only an estimate, and we estimated exactly like that.
Yeah.
So we investigated. So what couples to what, and how many kind of entries does this tensor need to have?
Again, pardon the naive point, but maybe an HDF approach would help you because you can do something like self-consistent bond, or even just for coherent, the inversion.
Yeah.
You have really an infinite series coupled or covered. It's not, of course, it's not covering every
term,
term,
yeah.
but at least it's infinite. So there is very high orders of it.
Yeah, I mean, I definitely want to look into that.
Okay.
So it's
Okay, fair enough.
it's just
And
it has quite an entrance barrier, as we discussed.
yeah. I'm happy to help, of course. So that's very exciting work. And one last comment, it's maybe not so well known if you're not in that business, but there's a very systematic way to deduce, quantum corrections to drift diffusion or Boltzmann equation out of the NGF equations. So it's very, very systematic. So it will apply to any method that you will have. If you allow for perturbative treatment. If it's
Yeah, we
not
do. I mean, we do
perturbative-
perturbative treatment in
Right.
like most cases here.
Right, so if you had polarons, then it would work, but otherwise.
Otherwise, it's so we know this is all kind of perturbation.
Again, also happy to help in that if you're interested.
Sure, I am definitely.
Yeah, let me know. So I continue discussion.
Do you have any other questions for Michael? I think we can thank our speaker.